All right, so today we are going to talk about using a table to find conditional probability. So some of this is going to be similar to what we did yesterday. I need you up here. Okay, and the language is what's going to be really important. So the way something is being asked. So in this table, this is the domestic migration from 1995 to 2000. A person is randomly selected, and we're going to find each probability. We're going to write our answers as a fraction and a decimal, so you will need your calculator. So here we have different regions. These are the immigrants, which, do you guys know the difference between an immigrant and an emigrant? Yes. Good. The immigrants are coming in, the emigrants are going out. So in the first question, it says an emigrant is from the West. So the fact that it says an emigrant, it's given that they are an emigrant, which means we have to find the probability that they are from the West, given that they are an emigrant. So when we're setting up the total over the favorable, in this case, the total is the total number of emigrants and then our favorable are going to be the emigrants from the West region. Okay, so an emigrant is from the West. So what we're going to do is we are going to find the total number of emigrants, which would consist of the emigrants from all regions. So we're going to total up this column. Yep. And you guys have your calculators. Cam, is that your calculator?
I got it.
What'd you get?
Approximately 2.8.
No. How many emigrants did you get?
Oh, total number of emigrants is 11,656.
Good, 656. Okay, so that is going to be in the denominator. Okay, now, Cam, what'd you put for the number of emigrants from the West?
2654.
Okay. All right, so we have to write this as a fraction and as a decimal. Whenever you are writing them as a fraction, it does need to be reduced. In this case, what number do we know goes into both of them? 2. Okay, so we're going to cut each of them in half, divide by 2. We'll get 1,327 over 5,828. These are very large numbers. So when you are trying to reduce, remember your divisibility rules. So this does not have an even number on the top, so I know I can't reduce it by any even number. And then the next one I would try would be 3, but 1 plus 3 is 4, 4 plus 2 is 6, 6 plus 7 is 13, so 3 doesn't go in there. Another thing I would try, do you guys remember one of the strategies I told you to try if you're reducing? See if the top number goes into the bottom number evenly, and in this case it won't. So the reduced fraction is 1,327 over 5,828, and that is going to equal 0.23. All right, let's look at the next one. So again, we just have to pay attention to the language. So this one says someone selected from the South region is an immigrant. So we already know that someone is being selected from the South region. So we're finding the probability that someone selected from the South is an immigrant, given that they're from the South. So when we're setting this up, the total on the bottom is going to be all Southerners. So the total amount of Southerners. I put Southerns. Okay, and then on the top is going to be the immigrants from the South. All right, so let's find the total of all Southerners. Okay, so our region here, South, we're going to find this total. Okay, so the 5042 plus the 3243, and we should get 8,285. Okay, so then that's going to be our denominator, 8,285. From the top are going to be the immigrants from the South. All right, so KL, how many immigrants are there from the South?
5,042.
Good, so that's what we're going to put in the numerator. Okay, and then we're going to divide and round to the nearest hundredth. So notice it does say that you're doing this as a decimal. Make sure that you guys are rounding correctly too. So 5042 divided by 8285. Okay, so you're looking at the 8, that's what rounds it up. If it was a 0, you need to leave it as a 0 if it's not an exact answer. Yes.
I was gonna ask, we leave it in decimal form, we don't make it like a percentage, right?
Right, yep, so if it says to write it as a decimal, then you don't have to write it as a percent. Yep.
And if we do, would we get marked down or no?
Yes, if
Like,
it
we have
said to
decimal
write
and
it.
percentage, I'm saying.
Just follow the directions. All right, and then for C, now this one is worded a little bit differently. So this one says someone selected is an immigrant and is from the Midwest. If it has this and in it, okay, then your setup is going to be a little bit different. Okay, so if we're finding the probability that a person is an immigrant and Midwestern, then we're going to set this up over the total number of people. So everybody in the chart. And on the top would be somebody who is an immigrant and from the Midwest. So to find the total number of people in the chart, really, what could I do? I already have the total immigrants. Can we find the total immigrants and then just add them all together? Let's do that. Okay, so the total number of immigrants, I'll help you out, will be 11,655. And then your grand total is going to be 23,311. Okay, so that's what we're going to have in the denominator, 23,311. So if they're an immigrant and from the Midwest, we're going to find that box. So immigrant, Midwest, 2,951. And really, if the numbers were this large, where they're in the thousands, I wouldn't make you reduce that. Not that you could. Some of you probably know how to reduce on your calculator too, don't you? All right, and then D, someone selected is from the Northeast and is an immigrant. Okay, so again, it's saying that they're from the Northeast and they are an immigrant, so the setup is very similar to what we did in Part C. So on the top would be that they're Northeast and an immigrant, and that would have to be over the total. Okay, so we know the total is 23,311. Let's go back to our chart. So if they're from the Northeast and an immigrant, there are 1,537. This is a good time for you to divide and check to make sure if you are rounding correctly. And you should get 0.07. All right, and then for example 4. I like these kinds. So this has to do with cards. It does tell you that 2 cards are drawn from a deck of 52. Do you guys know that in a standard deck you have 52 cards? Because it might not always tell you that. So we are going to write down some standard things. So a deck of cards has 52 total cards. When we're doing this, we're going to determine whether the events are independent or dependent. And we're going to find the probability. Okay, so this says selecting 2 hearts when the first card is replaced. First, let's talk about, in a deck of cards, we know there are how many suits? 4. Okay, so 4 suits. So what does that mean? How many cards are there of each suit?
13.
Okay. Okay, and if there are 4 suits, that means if it's a queen, there are 4 of them. Okay, king, etc. Face cards are king, queen, and jack. All right, the first thing we're going to decide is whether it is independent or dependent. So, does the probability depend on something else? So A, selecting 2 hearts when the first card is replaced. Is that independent or dependent? Independent. Anytime it's replaced, it's independent. So selecting the first heart is not going to affect selecting the second heart. For B, you're selecting 2 hearts when the first card is not replaced. If it's not replaced, then instead of having 52 cards, the second draw you have how many? 51. Okay, and then for C, it says it's not replaced, so this would be dependent as well. All right, if you have an independent event, we know that you would multiply the probability of A times the probability of B. In this case, it says selecting 2 hearts. So this is the probability of drawing a heart multiplied by the probability of drawing a heart. So drawing the first heart, there's 52 cards. How many of each suit are there? 13. These are ones that you do have to reduce. And then because it is replaced, it doesn't change, so it is 13 over 52. Now, you have to reduce your fraction. You can either multiply straight across and then reduce, or you could reduce first. If it's 13 over 52, what does that reduce to? 1 out of 4. Okay, so then this would be 1/4 times 1/4, which would be what? 1 over 16. Okay, generally we will keep these as just fractions. You can always use a fraction unless it's unless you have different directions, unless your directions say otherwise. The other thing that you could do is you could multiply straight across. So 13 times 13 on top, 52 times 52 on the bottom, and then again you'd have to reduce. But if you use one of the strategies I taught you, that would go really quick. What's one of the strategies I taught you about reducing? Yeah, so if you took 2,704 divided by 169, you get 16. So it would be a quick reduction. All right, let's look at the second one. So selecting 2 hearts when the first card is not replaced. So what this means is you're finding the probability of drawing a heart, and then you're multiplying that by the probability of drawing a heart when a heart is already drawn. I'm just going to use symbols, okay? Drawing a heart when a heart's already drawn. Aww. Okay, so really, if you are thinking about this from a logic standpoint, let's think about the first one. We already know the probability of drawing a heart is what? Yep, 13 out of 52, which we are going to reduce to 1/4. And then the probability of drawing a heart when a heart is already drawn, well, if you drew a heart first, the total number drops down to what? 51. Okay, if you already drew a heart, how many hearts are left? 12. Okay, so you have 1 less card in total because it's not replaced. Okay, and you have 1 less heart because a heart was drawn first. Okay, so now we're gonna multiply. All right, so what we have here is 1/4 times, what goes into both 12 and 51? 3, right? Because 5 plus 1 is 6. So if you divide by 3, you have 4 on top. What's 51 divided by 3? 17. And then instead of reducing later, reduce now. What happens?
4 is canceled.
Yeah. So you just have 1 over 17. You guys want to do the last one by yourself? Some of you already did. Okay, so a queen is drawn, is not replaced, then a king is drawn. So you are finding the probability of drawing a queen times the probability of drawing a king when the queen has already been drawn. All right, so then the queen, how many queens are there? 4. If it's not replaced, your total drops down to 51. Okay, what's the probability that you're going to draw a king given that a queen's already been drawn?
4.
It's still 4, right? It's not going to affect that part. Okay, let's reduce. So 4 out of 52 is going to be 1/13 multiplied by 4 out of 51. Now, I want to show you how you can think about the reduction without using your calculator. We know that 51 from above is what times what? Because didn't we reduce this? Yeah, it's 17 times 3. So if you have 4 on top, the only thing that goes into 4 is 2 and 4. Is 2 or 4 going to go into any of those? No, and I wouldn't break it down further because 13, 3, and 17 are all prime. So then when you multiply across, this is just 4 over 13 times 51.
6.
Yeah. Ooh, those odds are getting steeper. Okay, good. So your homework is a worksheet that I'm going to pass out. Well, really, it's like a packet. And then I will be checking that tomorrow.